Hello students, how are you? I hope you are doing well. So today we are taking a topic which is elevation in boiling point, and we'll do the derivation by the use of Clausius-clapeyron equation. Okay. So let's suppose initially we have a pure solvent, and pure solvent has a vapor pressure of P naught B and have a boiling point of T naught B. But as we know that the solution is made up of solute and solvent, it don't have a same vapor pressure and boiling point. So let's suppose this solution have a vapor pressure of Ps and Ts would be the boiling point of solution. So okay, so we have draw two curves here. The white one is for the solvent and the orange one is for the solution, P versus T graph. So we can see that at any temperature, let's suppose basically what is boiling point? Boiling point is the temperature at which the vapor pressure would be equals to the atmospheric pressure. So let's suppose atmospheric pressure is 1 atm. So at this 1 atm, the solvent line touches 1 atm. So this is the P naught B. It means this whole pressure 1 atm would be P naught B. Okay. So let's suppose T naught B is the temperature when the solvent vapor pressure becomes equals to P naught B, and which is 1 atm. Okay. So let's suppose this is T naught B, but we can see that at T naught B temperature, pressure of solvent is P naught B, but solution does not have the same pressure. Its pressure is Ps. This is the vapor pressure of solution. But it means we need to heat it more so that we can get pressure equals to P naught B. It means initial pressure which I can write is right at P1. Initial pressure of the solution is Ps, and final pressure to get boil would be equals to P naught B. Okay, so I will denote solvent with A. Let's suppose I can use that. I can denote solvent with B. B would be the solvent and A would be solute. Okay. So in such case, we can use Clausius-clapeyron equation. So what this equation suggests us that natural log of P2 upon P1 would be equals to delta H upon R 1 upon T1 minus 1 upon T2. Here delta H is basically molar enthalpy of vaporization. Molar enthalpy of vaporization. It means if you have 1 mole of solvent, then the amount of heat required to evaporate that solvent is called as molar enthalpy of vaporization. Okay, it means this is for 1 mole, and LV is the latent heat of vaporization. Latent heat of vaporization is defined for the 1 gram of solvent. So it would be equals to delta H, which is for 1 mole, divided by MB, which is MB here is molar mass of solvent. Okay, so now we recollect it. The initial pressure of solution would be Ps. Okay, final pressure of the solution to get boil should be P naught B. and this P naught B will come at a temperature of solution which is, let's suppose, Ts. Ts is the boiling point. Okay, so we will put this into this equation, Clausius-clapeyron equation, and it will look like natural log P2 is P naught B upon Ps is equals to delta H upon R. Initial temperature would be T naught B minus 1 upon Ts. Ts is the final temperature at which basically your solution will get boiled. Okay, so we assume a dilute solution. For a dilute solution, moles of solute is very less than moles of solvent. Okay, so what I am doing, I am basically taking an inverse of this equation, which could look like natural log Ps upon P naught B would be equals to minus of delta H upon R 1 upon T naught B minus 1 upon Ts. Okay, so it can be written as delta H upon R. I can take LCM and it could look like T naught B into Ts minus T naught B, natural log of Ps upon P naught B. Okay, so as we have assumed that our solution is dilute, so for dilute solution, you will see there is no much change in the boiling point of solution. So what we can write, T naught B would be approximately equals to Ts, and delta TB is basically this thing. It basically denotes you elevation in boiling point, which is delta TB Ts minus T naught B. Okay, so natural log Ps upon P naught B would be equals to minus delta H upon R. It would be equals to delta TB upon, because what we have assumed is that T naught B and Ts is approximately equal, so we can write it T naught B square. Okay, so as you know, Ps is the solution vapor pressure, which will be equals to P naught B into mole fraction of B. Okay, so I can write Ps is equals to P naught B into mole fraction of B upon P naught B minus delta H upon R into delta TB upon T naught B square. So you can see that P naught B will cancel out. So natural log of chi B, which is mole fraction of B, is equals to minus delta H upon R into delta TB upon T naught B square. So as you know, for the binary solution, for the binary solution, what we can write, mole fraction of A plus mole fraction of B would be equals to 1. So natural log of this mole fraction of B would be equals to 1 minus mole fraction of A. It will be equals to minus delta H upon R delta TB upon T naught B square. Okay, so I hope you know that natural log of 1 minus x would be equals to minus x if x is very small, because we have assumed that the solute concentration is very less. So we can write natural log of this thing, natural log of 1 minus mole fraction of A would be equals to minus of mole fraction of A, which is equals to minus delta H upon R into delta TB upon T naught B square. So you can see that negative and negative will cancel out each other. So from here I can find out delta TB, which is elevation in boiling point, would be equals to mole fraction of A into R times of T naught B square upon delta H. Okay, So after this, we can open this mole fraction of A. How? See, delta TB would be equals to what is mole fraction of A? It will be equals to mole fraction of A, moles of A upon moles of A plus moles of B, okay, into R times of T naught B square upon delta H. As we have assumed that moles of A is very less than moles of B, so from this denominator we can neglect this part. Okay, so delta TB would be equals to moles of A upon moles of B, R times of T naught B square upon delta H. Okay, so see what we can write after this. Moles of A, how you can write the moles of B? It basically equals to given weight of B, which is solvent, into molar mass of B, okay, which is equals to R times of T naught B square upon delta H. Okay, see, now delta TB would be equals to, see what I can do right now, this molar mass of solvent, I can take it in the denominator of this delta H. It would look like this, right? And now you know this delta H into divided by molar mass of solvent would be equals to latent heat of vaporization. So delta TB is equals to moles of A upon weight of B, which is solvent, R times of T naught B square upon latent heat of vaporization. So see what I am going to do after this. I am basically multiplying and divide by 1000. Let's have 1000 here and 1000 here. So what you can see here is that this thing is basically molality of solution. So delta TB is equals to molality into, this would be R T naught B square upon 1000 into latent heat of vaporization. So here we have derived the elevation in boiling point formula. And you can see that the elevation in boiling point is basically directly proportional to molarity or the concentration of solute in the solution. Further, R is universal rate constant. This is a constant value. Boiling point of pure solvent is constant, latent heat of vaporization is constant, and 1000 is constant. So this whole constant can be written as Kb, which is equals to R T naught B square upon 1000 into Lv. So this constant called as ebullioscopic constant. Okay, ebullioscopic constant, or we can say it molar elevation constant. I guess this is done for this video. Thank you very much.